Okay. So we did that for u and v, right? We found out a vector. It was 3, 5, 7, or 3i plus 5j plus 7k. We crossed them the other way and found out that we got the complete negative of that. We got -3, -5, -7, right? But that's just coming out in the complete opposite direction. It's still sort of, like they're in line with each other. And a very important thing to remember that I don't even always remember is that when you do this sort of determinant stuff, that there is always an extra negative sign on the j term because of reasons. And last, we found out that a vector crossed with itself is the zero vector. Just because, what would it even mean for how would you even get one answer for, the question as to, what vector is orthogonal to two vectors if those two vectors are just the same vector, or even just going in the same direction. And there is none, so what you get out of the cross product of crossing a vector with itself is the zero vector. Okay. So you don't have to remember these explicitly. So as we saw, depending on the way that you cross two vectors, you can either get, the cross product or the negative of that same cross product. You'll get one vector if you do u cross v, but you'll get the negative of that vector if you do v cross u. Finding the cross product is distributive over addition. Everything that we're going to talk about is distributive over addition. Addition is just one of those things that operations are always distributive over, whether you're talking about numbers or matrices or the dot product or the cross product. If you're doing something to a sum of two vectors, it's going to distribute over them. If you have a constant times a cross product, it's the same as if the constant were on one vector, were multiplied by one vector, or if the constant were multiplied by the other vector. It doesn't matter where you put the constant, in front of the cross product, in front of one of the vectors, in front of the other vector, it's all going to be the same. A vector crossed with the zero vector is 0. A vector crossed with itself is 0. And if you take a vector and dot it with a cross product, it's the same as if you cross the first two vectors and then dot it with the third. So ultimately, if you have three vectors, u, v, and w, in that order, it doesn't matter which of the first two or the last two that you cross first and then dot with the remaining one. As long as they're in order u, v, w, it doesn't matter which, whether you cross u and v first or v and w first. I will say that the cross product does have to happen first because if you remember, the dot product returns a scalar. What a dot product produces is a scalar. So if you were, for example, to try to dot these two first, you'd get a scalar, and you can't cross a scalar with a vector. So you have to do the cross product first. But it doesn't matter whether it's u cross v or v cross w. and then you just dot it with whatever is remaining, and they'll be equal. Okay. And we'll talk a little bit more about like what this is later. Okay, so we already know this. The vector that we get from crossing u and v is orthogonal or at a right angle to both of the vectors that you used. It's at a right angle to both. The magnitude of u cross v is equal to the magnitude of u times the magnitude of v times the sine of the angle between the two vectors. I'm sure that there is a nice mathematical explanation for why this is, but even if I knew it, I'm not sure that it'd be relevant. Orthogonal?
Yeah, is that supposed to...
Yeah, it means perpendicular or at a right angle. Yeah. If you have two vectors and you cross them and the cross product turns out to be the zero vector, 0, 0, 0, the reason that happens is because the two vectors are going either in the same direction or in the complete opposite direction. Either way, they're parallel to each other, or in other words, one is a scalar multiple of the other. That happens if, for example, v is 2 times w or 1/2 times w or 1 times w. Just sort of if they're oriented in the same direction, crossing them will give you the zero vector. And that's because, like, normally the cross product happens like, you got two vectors in space, and here, let's call this u, let's call this v. This is u cross v, because this is 90 degrees and 90 degrees. No word on what this this angle can be anything, or like almost anything. But this vector that's produced by crossing is orthogonal to both of the vectors you started with. Now, how to interpret that when both vectors are just sort of going in the same direction? If this is u and this is v this time, there's a if they're just going in the same direction, that's 90 degrees. That can be 90 degrees. That can be 90 degrees. Like, there's not one vector that's going to come out and be 90 degrees to two vectors if the vectors are just this, going in the same direction. So nothing comes out of this. Only the zero vector comes out of this. If you try to cross them. And the most geometrical of these things is that the magnitude of u cross v. So always this is always supposed to be a positive number. The magnitude of u cross v is the area of a parallelogram where u and v are the sides. So if, let's say that u is here and v is here. Okay. Now crossing them will, I'm just going to say that comes out this way, sort of towards the front. Right, and this is supposed to be u cross v. Now, if you take u and v and sort of make them the sides of a parallelogram, the area of that parallelogram is equal to the magnitude or norm of the cross product of that vector. The magnitude of this is going to give the area of this parallelogram. And that actually follows from the second property, where the magnitude of the magnitude of the cross product is equal to the magnitude of u times the magnitude of v times the magnitude of the sign between them. And there's you can derive the fact that this gives the area of the parallelogram has to do with the formula for the area of a parallelogram, which is just base times height. The base is clearly v, and the height would be sine theta times u. But that's just where it comes from. But it is the area of the parallelogram having u and v as sides. And yeah. So this is v, this is u, and then this will be the magnitude of u sine theta if this is theta. And you can sort of find that by sort of making a right triangle here. This side will be the sine of u times the sine of theta. Because the sine is opposite over hypotenuse, u is the hypotenuse, so multiplying it by u will give the opposite side. So just the magnitude of u times sine of theta is an expression for this opposite side, which gives the height of the parallelogram. And taking this and multiplying it further by the magnitude of v gives the area of the parallelogram. Not that that's it's not really important to know where it comes from, but that's where it does. But just be thinking, okay, magnitude of the cross product gives like whenever you hear the word parallelogram, you should be thinking cross product. Okay, if you need to remember the direction that u, v, and w, u, v, and u cross v come out, you can use, like many things, in physics and engineering, you can use the right-hand rule. And that's just to say, if you have u, and you have v, and you cross them, your answer to whether it comes out this way or this way, right? Because there are two options for how it comes out, depending on the order that you cross them in, is that it's handed, in that if you have u cross v, it's going to follow this sort of order: u, v, u cross v. And that sort of, you just take your right hand and sort of, the direction of it. It's going to go towards, it's going to hit u, well, you're going to start at u, then it's going to hit v, then it's going to hit u cross v. Yeah, if you did it the other way around, yeah. That's all you need to remember. Here's a drawing of a hand. Here's a drawing of a right hand. There. Okay. But other vectors that do this are actually the three standard vectors, like the I, j, and k. If you start at I, you can use the right-hand rule to determine then that you're going to hit j, and that k, which is actually the cross product of I and j, is going to go up. So they kind of basically, two vectors and their cross product kind of follow the direction of I, j, and k.
Is it like similar to the right-hand rule for physics?
I feel like there are a lot of right-hand rules in physics, like a lot of different ones. But yes, it does have to do with you sort of look down your thumb and then just which is pretty much how all those rules work. Yes.
With their cross product, would it always be like the z-axis?
Oh no, this could easily just this could yeah, if I can't rotate this, but if u was here and v was here, for example, you could still follow the right hand rule, even if it's not oriented in this sort of perfect way. U, v, and then you hit u cross v, so it comes out this direction, as opposed to, say, this direction. So no matter what way it's oriented, basically it goes in a counterclockwise direction. Yeah, irrespective of its actual orientation. Yeah. So you start at u, you hit v, and then that's where u cross v is going to be. Okay. All right, so find a unit vector. So first, a unit vector is a vector with magnitude 1. And it's found by you find unit vectors by first, finding a vector that goes in the direction you want, and then taking that vector that you found and dividing it by its own magnitude to sort of shorten it to be a length of 1. So if you want to find a vector that is orthogonal to some other vector, that immediately your mind goes to cross product. All right. So in order to find the cross product, we got to make up one of these. I, j, the first row being I, j, k. Second row being 1, -4, 1. And the third row being 2, 3. And because there is no k term, 0. Okay. So obviously you won't have to copy this over, because you can just use your finger to block it out. But first, for the I component, we cross out the row in the column that has I in it. Then we find the determinant of the remaining 2x2 matrix. So that's AD minus BC. So -4 times 0 minus 1 times 3. So that's 0 minus 3. So -3. Then you do the same for j, keeping in mind that the j is going to have an extra negative sign already. Let me just put that there right now. So that's going to be 1 times 0 minus 1 times 2. So that's 0 minus 2, or negative 2. Make sure to include the negative sign. That's sort of always going to be there in front of the j term. Then last, for the k component, that's going to be 1 times 3 minus negative 4 times 2. So that's 3 plus 8. So plus 8k. All right, so this vector that we have, well, so let me just, negative 3i plus 2j plus 8k. That is in the correct direction, but it is not a unit vector because it does not have a length of 1. It has a length of, I guess, like 7, square root of 77 or something like that. I mean, I guess we'll find it out. So this is in the correct direction. Because it's orthogonal.
Yeah, it should be 11k, right?
Yeah, yes, it should. I was thinking 3 plus 8, and then I guess I just wrote the 8. Yeah. Damn. Yeah. One day I'll stop making mistakes. Like there'll just be one day where I'll never make a mistake ever again.
Just wake up and you're perfect.
Yeah. Okay, so that vector is in the correct direction because it is orthogonal to u and v. You can just sort of take it for granted that it is. I mean, if you wanted to check that it was, I suppose you could, use the dot product. If you take the dot product of two vectors and they're orthogonal to each other, the dot product should come out as 0. But that's only if you really wanted to check it. So this is in the correct direction, but it's not a unit vector. Yet. Okay, so minus 3, 2, 11. Okay. So we're going to take that vector, negative 3, 2, 11, and we're going to make a unit vector out of it. We're basically going to divide it by something, right, to sort of shorten it to where it is a unit vector. So that was negative 3i plus 2j minus 11k. No, plus 11k. Right, yeah. Okay. So this is not a unit vector. But if we take this, and you can write it in the vector form as well, with the little brackets. It doesn't actually matter. But if we take this vector and we divide it by its own magnitude, that should shorten it to where it is a vector with length 1. Right, that's always the way to make a unit vector, is to take whatever vector that goes in the direction you want and divide it by its own magnitude. Now its magnitude is going to be the square root of the sum of negative 3 squared, 2 squared, and 11 squared. Which just comes out as the square root of 9 plus 4 is 13. 13 plus 121 is 134. Yeah. So the square root of 134. And as to whether 134 has any square factors, it can be simplified. Divided by 2, that's 67. 67 is prime. Okay, yeah. Yeah, so 134 is like the most reduced that you're going to get this radical. So if you want to write it as separate components, which, I suppose you do, the coefficient of the first, the coefficient of I will be negative 3 over the square root of 134. Plus 2 over the square root of 134. Plus, j. Yeah, let's go to j. Plus 11 over the square root of 134. Okay. So that is a unit vector, and it goes in the same direction, right? Because it's just the cross product that we had, but scaled down. It goes in the same direction as our cross product, meaning it is both a unit vector and orthogonal to the two vectors we started with. Now, if this is an acceptable answer, another vector that is orthogonal and a unit vector would be positive 3 over square root of 134 I minus 2 over square root of 134 j minus 11 over square root of 134. Okay, because that just goes in the complete opposite direction, right? But it's still, it coming out in the complete opposite direction makes it still orthogonal, and it's still going to have a length of 1. So there are actually two answers to this. There are two vectors that are of length 1 and orthogonal to the two given vectors. So either one of these would have been fine. Because this is just take that. It's the negative of that vector will also just be, it'll also have those properties. Okay. So one of the reasons to use a cross product is so in physics, of course, there's the sort of early part of physics where you're just talking about just sort of forces and how they're acting on a thing, and you don't need the cross product for that, because that's just decomposing vectors and adding them up to find their total, or like the resultant vector, to find the total force on the system, or whatever they call it. But when you start talking about rotational force, all of a sudden that starts being not enough, because when an object rotates, if you were to consider it as its center of mass doesn't move, so just adding up vectors is not enough, because in terms of actual movement through space, something that's rotating does not move at all. At least in in terms of a moving object, right? It doesn't move at all. So you need a way to describe this sort of rotation, and you need more than just take these vectors and add them up. And that's what the cross product is for, and that's what talking about torque is for. Torque is just rotational force, essentially. And when something rotates, the way that you mark torque in a free body diagram is that the torque is coming out orthogonal to the direction of rotation. And it's a vector that's orthogonal to the direction of rotation. And because of that, the cross product becomes actually pretty useful, because that's what the cross product does. It allows us to find orthogonal vectors. Okay. So let's say there's an object in space, and a force is being applied to it in order to make it rotate, not move, in space, but just rotate. If you consider the direction of that force as one vector, and the distance from the axis of rotation to where the force is being applied as another vector, the cross product of those two vectors will give the moment of the force about the point of rotation, which is right here. So this is m, and the reason it's going the direction it is because m is the cross product of this one vector and this other vector. And if you measure the magnitude of that cross product, that's going to give essentially how much it's rotating or how much it wants to rotate. So the bigger m is, the more it's rotating, essentially. Which makes sense. Sorry, what?
M is a vector.
M is a vector. Yeah.
Then that's just the equation for torque.
Yeah. Yeah. So as a yeah. And again, this this also uses the right-hand rule, which you might have seen. Because it is useful, when you're making a free body diagram to know in which direction, the torque or the moment of the force, comes out, either this way or this way. But if you follow the right-hand rule and you just sort of pretend that F is right here, then take the vector PQ, start at the vector PQ, cross it with F, and then that means M is going to come out on top. So that's actually all that we're going to talk about that. It can be used for this. We're not actually going to. Yeah. All right. And the last thing that we need to talk about in terms of this cross product stuff before we start getting into equations of lines and planes in space is something called the triple scalar product. Okay. All right. So this is going to be kind of an extension of how, and I know I only said this like 30 minutes ago, but how the magnitude of the cross product gives the area of the parallelogram This is going to be sort of like a similar thing, but in 3 dimensions. So there is this expression, right, where you have u, v, and w. You cross v and w first to make a vector, right? V cross w is going to be a vector. And then you take u and dot it with that cross product vector, and you're going to get a number. And that number is called the triple scalar product. And if you remember, it also was equal to if you took u and v and crossed them, and then last dotted it with w. It doesn't matter which order you do these, as long as u, v, and w are in that order, and you do cross product first. So it's very similar to finding the cross product in general, because you still got the v and the w here, right? So if I were to, not that you guys need to know this again, but if we just sort of block this out here, if we were just talking about the cross product of v and w, that would actually look like this, with the I, the j, and the k, right? Just sort of as we're used to. And we get a certain value for the I, a certain value for the j, and a certain value for the k, or a certain coefficient for the I, j, and k. But if we were to then take whatever those, whatever the I, j, and k of the cross product were, and then dot them with u, well, we'd be multiplying the I component times the first component of u, right? Because that's how the dot product works. You multiply the first component with the first component, second component with the second component. So the I component would just get multiplied by u1. The j component would get multiplied by u2, and the k component would get multiplied by u3. So in the end, it's just easier to throw the u1, u2, and u3 up here in the first row, because you're going to be multiplying by all of those in the end anyway. And so it ends up being this, just this sort of u1, u2, u3 on the top instead of I, j, and k. But it still works, the same way. You still, block out one row and one column, and you find the determinant of the remaining 2 by 2 matrix, and those will be your coefficients for, u1, u2, and u3, and you'll just add them all together at the end, which we'll do. But the number that comes out of this process is the volume of not a parallelogram, because a parallelogram is 2 dimensions, but a parallelepiped. Yeah, which is just a 3-dimensional shape having a parallelogram as all of its faces. Right, so where you could, whereas in 2 dimensions, you can talk about a parallelogram that has, 2 vectors as its sides, right? And so you just sort of translate them to make a parallelogram. In 3 dimensions, if you have 3 vectors, you can make a 3-dimensional shape out of this by just translating a bunch of these over and over. And last. Yeah, so it's basically just this sort of weird oblique, like squashed cube, essentially. You're just taking a cube and just, but that's the shape of the 3D analog of a parallelogram. But this process of finding the triple scalar product gives the volume of this shape. Which is just stated formally here. The volume of a parallelepiped is given by the triple scalar product, u dot the cross product of v and w. And the absolute value bars are here just because sometimes what can come out is a negative number. All you care about is the magnitude of that number. So we'll give this a try. Okay, so there are three vectors, and you can make a parallelepiped out of them. And although this is the form of the triple scalar product, probably more important to remember is that it literally just is. The triple scalar product is just this whole thing. 3, -5, 1, 0, 2, -2, because there's no I term on V. Sorry, here are the three vectors. And 3, 1, 1, yeah. All right, so this is from U, this is from V, and this is from W. Let me take this over to the left. Let me take this and copy it over twice. Okay, so what we're going to do every time is we're going to sort of do this very similar to the cross product in general with the whole IJK stuff. So we're still going to block out, that first row, first column, but we're just going to keep an eye on this. Now, normally, so before, all the times that we found the cross product, there was I, J, and K across the top, and when we did this first one, over here was I, and whatever number we got out of this became the coefficient for I. Now that I has been, now that instead of I there's 3, we're going to take whatever we get here and multiply it by 3. Same way that we were multiplying it by, the standard vector I before. But we'll just take a look at this. So 2 times 1 minus -2 times 1. So 2 plus 2, right? So which is 4.
So 4 times 3?
So just 12. And I want to say that just like before, there is that extra minus sign in front of the middle term. But we're going to do the same with the top row, middle column. Boy, I kind of didn't leave myself enough space for this. Okay, so 0 times 1 minus -2 times 3, so 0 minus -6, so 6. But 6 times -5. So -30, keeping in mind that there is that extra negative sign there. And we're going to do the same with, you know, k used to be here, but now it's just 1. But we're going to take whatever we get out of the determinant of this 2 by 2 little subset. 0 times 1 minus 2 times 3. That is negative 6. And that negative 6 is going to get multiplied by 1. So ultimately it just becomes minus 6. Okay. So what we get is 12 plus 30 minus 6, which is 36. Right? Yeah. 36. And you know, if it were negative 36, we just take the absolute value and get 36 anyways, but okay, but very much the same as finding the cross product in general, just instead of them being the coefficients for I, j, and k, you're gonna take these determinants and multiply them by, you know, 3 or negative 5 and 1, but everything else is the same. You're just, you know, it's just the top row is something other than I, j, k. So it's 36, I guess, cubic units is the volume of this thing. Okay, and there's a special case that happens that that this process gives 0 if all three vectors lie in the same plane. You know, if you look at this, then you know you can take any 2 vectors and imagine that they lie on a plane, and that's not a problem. But if all 3 are in the same plane, you don't actually have to remember much of this, like of this stuff. Let's say that all 3 vectors that you have are in the same plane, then let's say these are coplanar. Like they're just all like on a flat surface. If you try to construct a parallelepiped out of that, you're going to get a flat, you know, if they're coplanar, you're going to get a flat shape with 0 volume. That's all that that's saying. So if you got 3 vectors that are coplanar, trying to find the triple scalar product is going to give you 0 because if they're coplanar, you know, you're not actually making like a parallelepiped with any substance. You're just making this weird flat sort of, you know, you're making this degenerate parallelepiped that has no volume and it just is flat and all the sides are just, you know, yeah, touching each other and like all the sides are just, you know, okay. So the 2 things to remember from the previous section are just, first of all, well, I guess from the previous sections, just keep these in mind as we talk about this stuff. So if you want to check whether 2 vectors are orthogonal, you know, at a right angle to each other, use the dot product. It should equal 0 if they are orthogonal. if you want to create an orthogonal vector, if you want to create a vector orthogonal to two given vectors, cross them. When you cross two vectors, the vector that comes out of that process should be a third vector that's orthogonal to each of the two that you used. That's the two things to. Well, I guess when we start talking about distance, there's actually another thing from the dot product chapter. Projection, yeah, right. The projection onto V of U is given as U dot V over the magnitude of times V. Why is this a double bar? Okay. Okay, and that I believe, let me just verify that real quick. Oh, right, it's squared. Yeah, that makes more sense. Okay. I was leaving something off. All right. But the projection of U onto V essentially just taking a vector U and just sort of breaking it up into parts. The part of U, the component of U that is in the same direction as V, is given by the dot product on top, the magnitude of what you're projecting onto squared on the bottom, and in the end you just multiply it. In the end that's going to be like a coefficient. You multiply that times the vector V in order to get something that's the same direction as V, but just, might be shorter, might be longer, but it'll essentially be sort of, here's U, here's V. Let's say you want to break up U. It's kind of like, actually, what would probably be better is, it's essentially the shadow of U sort of projected onto V. So this right here, that is the projection onto V of U, or the projection of U onto V. Because we'll use these to sort of, when we're relating lines and planes and vectors that describe planes and all this stuff. Oh, yes.
So real quick, okay, U times V equals 0. So if those U times V is greater than 0, that would be a Q, right?
Let's see, if it was positive, that means the cosine is positive. Yes. Yeah. If it equaled exactly 1, that means, wait, sorry. Okay. Wait, what did you say?
I said because U times V equals 0, so then if it was U times V greater than 0,
yes.
Make it a Q and stuff like
that? Yeah. If it's from 0 to 1, that means that the the cosine, the x, right, of the angle is positive, and so it can go from 0, which we're talking about when they're orthogonal, to 1 when they're exactly the same vector. Yeah. If they're negative, that means it's going like this. I can't bend my thing. It's going like this, and that's going to be obtuse, possibly all the way down to -1 when they're going completely the opposite direction.
Thank you, Professor. The homework calls for it.
Okay, so these are 3 things to keep in mind, I suppose, as we talk about this. Okay, so we're gonna move from vectors to lines and planes, and lines are similar to vectors, but they're not exactly the same. But we're going to use vectors, to describe these sort of these 3-dimensional mathematical objects. We're going to learn how to represent a line, a plane. We'll learn how to draw a plane, and we'll use all of this stuff to start relating lines, planes, and points in space together. Okay. All right, so first we're going to start talking about lines. I mean, I guess the lowest thing we could start talking about is points, but I mean, you guys know what points are, so we'll skip over points and go directly to lines. Now, lines are not the same as vectors. So, okay, so consider the line L that goes through a particular point, right? And you'll know it's a point because it will be preceded with a P. And it's going in a particular direction. It's not the same as the vector ABC, but it's parallel to it. It's going in the same direction as the vector ABC. That vector that it's parallel to, that describes its direction, is known as a direction vector for that line. Now, we always take vectors to be starting at the origin, but the same is not necessarily true for lines. Lines can be anywhere, in space. And, if a line is going in the same direction as another, but it's, slightly shifted, if it's existing sort of somewhere else in space, those are going to be 2 different lines. So they're a little unlike vectors in that way. They're not always located at the origin, and for lines, the mathematical objects that we know as lines, it does matter where they are in space, not just their orientation. So the coefficients of, or the components of V, that describe their direction, the direction or movement in the X, Y, and Z directions are known as direction numbers. They're, not really all that crazy. Points. What's the vector PQ? Okay, so one way to describe this line is to say that it essentially starts at this point and it goes off forever in either direction. So one way to think of it is that there is a point that the line has with a particular X, Y, and Z, and that it just goes off in the direction parallel to a particular vector forever in this direction and forever in this direction. And the direction that it's a straight line, so that direction is always going to be the same, and it's always going to be parallel to the direction vector. So, so basically a line is defined by having a particular point in the line and also having a particular direction. Those are the two things that you need to define a line: a point and a direction that it is, a point that is on the line and a direction that the line is going in. This part is not what you need to remember, but let's just skip this. Okay. This is what to remember. Okay. So you can describe a line in this way. A line L parallel to a vector, or going in the same direction as that vector, that has a particular point in it. You can represent it by the parametric equations x equals, right, and that x is just going to be like the variable x, equals the x of the point plus a times t. A is the direction in the x direction. Y equals the y value of the point plus b times t, and z equals the z value of the point plus c times t. So essentially you're sort of breaking it up into, where is the line in terms of x, and how far is it moving in terms of x? Where is the line where's the line in terms of y, and how fast is it moving in terms of y, and where is the line in terms of z, and where is it moving in terms of v? Okay. If a, b, and c are non-zero, then you can sort of solve for t. What you do is you can take this and say, okay, well, from this, x minus x1 divided by a, that's t. Y minus y1 over b, that's t. And z minus z1 over c is t. And because these are all equal to t, they're also all equal to each other. And you can get this method of describing a line. These are known as symmetric equations because, well, they're symmetric with, the format of it is symmetric with respect to x, y, and z. So these are two ways of describing a line. One where each component is described separately, and this set of symmetric equations where they're all sort of described in tandem. Yes.
Like A, B, and C, and T represent.
Oh, so let me try drawing something in space. Okay. Here's x, here's y, here's z. Okay. It's hard. It'll be hard to get a perspective on this, but let's say there's a line just sort of floating out in space. And let's say that this right here is the point, I don't know, oops. It's a point, right? So I should put a P. 1, for the x, no, like 2 for the x, 1 for the y, and 3 for the z. Like let's say that's the point 2, comma 1, comma 3 out in space. And the direction that this, that it's sort of starting at this point and sprouting out from, that direction can be described by the vector. Let me say that that's moving, I don't know, it's moving in the x direction. So v, let me not use this color. Okay. This line is parallel to the vector. It's going in the direction of the vector. Let's say 3. How far is it moving the y? -1, 2. Okay, this is a, b, and c. They're the components of the vector that describe the direction it's moving in. So this line can be described, one way to describe this line would be the line 2, right, because it starts at an x value of 2, plus 3 times t. Actually, let me not use this. Okay, so this line can be described by the 3 equations: x equals 2 plus 3t, because the point, you can start at the point where the x value is 2, and you know from the direction vector that it moves 3 as t goes up. T is just time. I mean, it's not like time is really passing in this world. It's just a variable that can be a whole bunch of different numbers to describe like the movement of where the line is, like just so that you can get all the points on the line. And let me just talk more about that after this. Y equals 1 minus t, because it starts at a y value of 1, and the direction vector says it sort of moves in -1 in the y direction. And z equals 3 plus 2t, because it starts off at a z value of 3 and it moves 2 in the z direction. Now, what's important are not actually like, the important thing is the ratio of these numbers to each other, the 3 to the -1 to the 2. Because there are other vectors that have the same direction. The direction vector could have just as easily been 6, -2, 4, or 9, -3, 6. Like it can be any vector that's going in the same direction. And so these numbers could have been, 6t, -2t, and 4t. Because all that's important is the ratio of the change in x, the change in y, and the change in z given by the vector. So this is actually not the only way to describe this line. I mean, you could also have it moving in the direction -3, +1, and -2. That would create the same line. So these equations of lines are not unique, but that's what the A, B, and C mean. They're altogether they describe the particular direction in which you're sort of starting at the point and sort of shooting out. particularly because you can't just have a point and make a line from that. Because if all we had was this point, you can make a bunch of lines that go through it. You know, you could have this line or this line. You know, there's no way to tell, right? So we need some extra information other than just the point. And that information is the direction that the line is moving starting from that point. And that's what this is for. And that's what A, B, and C, you know, that's what A, B, and C are for. Yeah, it starts at the point. It starts at the point that you know is on it, but it does go in the same direction as that vector. Right? That vector describes the line's direction. Okay. So we'll find a way to describe this line right here. We know a single point that it goes through, you know, a single point that this line occupies. And we also know that the direction it's going can be described by the vector 2, 4, negative 4. Or, you know, that it's parallel to this vector. And, you know, as I was saying before, it's also, what this means is it's also parallel (1 to negative 2), or, you know, 4, 6, negative 6. There's an infinity of vectors, you know, because like there are a whole bunch of vectors that are going in the same direction. Like you can just make a new vector that goes in the same direction by taking a vector and multiplying it by whatever you want. So there's nothing unique about 2, 4, negative 4. There are an infinity of vectors that move in the same direction. But we're just going to use 2, 4, negative 4. Okay. So we'll use this as A, B, and C. This is the vector that describes the line's orientation. And let's see, we know it goes through this point right here. So parametric equations are the ones where x, y, and z are all described separately. We can start with those. X is going to equal, like in the parametric equation for the line, x is going to equal the initial point, or the initial value, right? The initial x value of 1. And it's going to be plus 2 times t, because 2 describes the sort of movement in the x direction, you know, in this vector, from that directional vector. Y is going to be the same. You're going to start with your initial value of y. You know, you're going to start at the point, essentially, and you're going to add 4 times t to describe the degree to which it moves in the y direction, again from the directional vector. And z, you're going to start with the initial value for z. That's the, you know, that's on the point that you know, which, you know, this point. So that's an initial z value of 4, and to that you're going to tack on a minus 4t. So these three equations together describe the line. As far as I can tell this line extends forever, so wait, how do we write this? X is less. Okay, yeah. T goes from negative infinity to infinity. It's like, so the variable t is kind of like, it's kind of like how you use theta when you're talking about circles or sines or whatever. It's just that variable that is allowed to be a whole bunch of things that just sort of describes the path of something. Yes.
So is it like y equals mx plus b? It's just like an equation of a line, but with different.
Yeah, yeah. So these are parametric, particularly because it's kind of like y equals mx plus b, but with y equals mx plus b, y is dependent on x, right? These are parametric because it's not that one variable is dependent on another variable. X is not dependent on y is not dependent on z. There's none of that. What's happening is that x, y, and z are all dependent on a fourth variable, t. That's what makes these parametric equations. I think you probably, in calculus 2, you maybe parameterized some curves, possibly. But when all the variables that you have or that you're talking about or that you're interested in are all dependent on a fourth, like, additional variable, that's what makes something parametric or parameterized. It's the existence of this t. So these are parametric equations. Okay. Now, if we just solve for t in each of these, and once you have these expressions solved for t, just set them all equal to each other. Those are going to make the symmetric equations. So if we solve for t in each of these, we can get x minus 1 over 2 is going to equal t. Y plus 2 over 4 is going to equal t. And z minus 4 divided by negative 4 is going to equal t. So this last one you can write in a number of ways. You can take the negative sign, throw it in the front. You can multiply the top by negative 1. And, like, you can have 4 minus z on the top, and that'll let you have a positive 4 on the bottom. It won't actually matter all that much. But taking these three equations that are all equal to t now and setting them equal to each other will give you the set of symmetric equations that similarly describe this line. And so, if you do this process of solving for t and then just setting the equations equal to each other, sort of bypassing the need for t, these are no longer parametric, these are symmetric. It's parametric because they all depend on t. Okay. So these are the two ways to describe a line. Honestly speaking, the parametric way of describing a line tends to be better, or easier to work with. Okay. But essentially the idea is that you're starting at this point 1 comma negative 2 comma 4 out in space, and from there you're moving sort of like forwards in a particular direction and backwards backwards in like the opposite direction, and sort of create a line through all the points that you pass through in doing so, right? Because you sort of just go this way forever and go that way forever, it sort of creates a line. Okay. I guess we'll finish this up on Monday, hopefully. Alright. So I will see you guys then. Yeah.